Next up, we have Michael Cerna of Firefly Aerospace, presenting Firefly Alpha ground software from test to launch. Michael, it is all yours.
Excellent. I assume I'm unmuted.
We can hear you just fine. And Jason, if you can turn off your video. Thank you.
Okay, so here's roughly what I'm going to cover today. I view our ground software at Firefly as being an evolving technology from what it amounts to a desktop or lower level avionics component test system. And then we scale it up at the test site or test stand, where we add many more IO points to support full vehicle loading and also control both at the test site and at the launch pad. And then finally, we use GSW for required certification or safety certification tests. To begin, this is all about ground software. You guys being flight software pros, the list on the left is pretty common, and I work with work closely with the flight software team, of course. For ground software, it's everything that's not all software really not running on the rocket, and yet dealing with the measurement aspects of what it takes to test and launch a rocket, including a lot of data acquisition, IO, digital IO, telemetry and vehicle interfacing, lots of GUI work, controlling, commanding, command authentication, and of course, data saving and data distribution. So in the beginning, so we have obviously desktop avionics component testing going on now. And in this typical scenario, you have a avionics component that you place inside of a chamber to test maybe how it performs under heat, duress, or vibration. And then we would basically would be centered around or controlled via one simple control computer. You may have data acquisition reading response from the device while it's being tested, or also we might control power supply to set some levels on the device. And in the background, we often would be running Python scripts to simulate some other part of the system that needs to stimulate the avionics component. We often have other measurement devices hooked up, like a spectrum analyzer, where we might capture data there and control it. All of it generally is networked, shown in the blue lines, typically using UDP protocols. Again, we have some data saving and plotting while the test is being run, and we would like some ability to remotely monitor the test. So that's the basics of software for avionics component testing, or a system for avionics component test. And then when we go out to a test site, we grow up that system. So we evolve our basic measurement system into something that's appropriate for just basically a much larger channel count. We have now more than many computers involved. We have many consoles that would be monitoring a GUI. We have data acquisition server devices, and these are machines that run, and basically they connect to the external real world, and we would convert our sensor data to be useful in the system. So lots of analog and digital input, and then we might control actuators via the DAC servers. Then we would have a power supply server where it's running on its own, and it's basically commanded to set certain power supply levels to provide externally controlled power to the system under test. If the system is a stage being tested, then it's also networked, and the stage server software runs on its machine and communicates to the stage in question or under test. There's also a notion of we need some sort of flow control or sequencing during our test. And so just going into a little bit more detail on the test stand, the data is collected from all these different DAC server nodes and power supply and stage server. With the stage server, it's often, we're talking about telemetry data coming from the stage. And this has to be communicated to the entire GSW ground software system. We then now, since we have this higher channel count system, maybe in the order of thousands of channels, we are in need of a data server. So that data server would read and distribute the data to the GSW system. And the arrows are drawn both ways because we often have to, now we're starting to affect the system via a commanding. And that's why we need to have authentication for commanding. So sometimes these commands would come from are controlled directly by a test operator on one of the consoles. He may do whatever he needs to be authenticated, and then he would set his output level. This could be any kind of actuator in the real world. It could be a valve state or pressure level, things like that. And then shown here also in the middle is these primary servers now need the ability to auto sequence. So whatever test operator may have manually controlled during parts of the early phases of test, we often have to then instrument or create an auto sequence script of sorts to then to automate the test under more rigorous sets of data control that a single person cannot perform adequately. When we extend the test stand to the launch pad, now we're really talking about a major upscale in number of channels, number of consoles, people sitting at the consoles who have controllability. Given that our channel count at the ground system has increased again to multiple thousands, we find ourselves in need of splitting up some of the from the servers into multiple primary servers. So now the data is served by maybe one or a few data server nodes. In addition, our timing is very critical. So we now we're running a precisely timed auto sequence engine on the command server. And the additional thing to note is that on every one of these nodes, we would want to store local data. So sort of high frequency or high sample rate data locally. We might distribute kind of a decimated version through the data server, through the consoles, and then the GUIs running on the consoles would render whatever they need to communicate to each of the test operators. Usually these test operators have their own domain expertise, and so they may flip to a page that is specific to fluids or propellants, things like that. In addition, now with the full rocket, we have the need to split up the servers into a server that might service the commanding from the ground to the vehicle during our tests on the pad before launch, and then also to as part of the all day long launch procedure. And then we also are in need of now distributing telemetry that is coming from a ground cabling connection. But once the rocket is in flight, now we need to be able to service multiple satellite streams, basically via web interfaces and sockets. So that's also brought in. Those channels are brought into our GSW system and distributed to the consoles. During these types of critical operations, we have the notion of configurable alarms, of course, where everyone or many in our company are monitoring, and they have their own special custom list of alarm values that they are checking for and get alerted. And then, of course, we have the commit criterion that helps to carefully move from one stage of launch to the next. The auto sequencing is critical. Again, the timing is really critical, so that's on its own command server node. So we basically evolved our avionics test into something that can be expanded on the test end, and then that is then expanded from test end to LAUNCHPAD. So we take what our rich classes have a lot of object data and a lot of functionality, and that will serve multiple network servers and specialized modules. And we would like to fold that back into the avionics test. And so we're talking about downscaling the classes, again, so that they run appropriately on a single test computer. The object data is much smaller, and what was in the original avionics component test software, perhaps a kind of a hand-coded state machine procedural sort of programming, we would like to displace that with an auto sequence. So we can basically use our ground software system everywhere. And finally, as part of launching, we work with the range and identify every possible hazard and create then a list of hardware or software mitigations. And then part of ground software's responsibility is to build in any kind of redundancy necessary and to test that. In the case of loss of connection, we often have to support a safe state for every one of the output nodes. DAC output we might hold to a certain state if we lose connection. And if we have, in terms of hardware, we might have for critical sensors, we may have three sensors that we would read from, and basically choose the ones that are in most agreement, as an example. And then in terms of proving out our functional operations, we have to run through safety critical certification tests where we test the auto sequence performance and timing and correctness. And we have to test whether the part of the system that broadcasts to the OSM, we have to make sure that that's broadcasting valid data so that they can make the correct safety calls. And then, we have to validate that our GUIs are appropriately implementing the command authentication through roles and locks. I think that concludes the presentation.
All right. Thank you very much, Michael. We have a couple of questions coming in. First one from Brian. Do you use pure UDP for the linkage, or do you run a messaging middleware like DDS?
We use UDP at all parts of the system where we have, well, in the avionics component test, we use UDP. And then between the vehicle and the telemetry servers and interface, we use UDP. And then we use a different kind of protocol, but we're trying to abstract that out right now so that we can explore the use of other communication protocols like UDP. So I would say we've abstracted the communication with the other nodes. That helps.
Okay. Mm-hmm. Yep. Next question from Colin Helms. Does the ground software have an interface to the flight computer for pre-launch load of gain schedule, cal data, etc.? And what process controls this?
Pretty much at startup, we have defined the state and basically the flight computer. What would you call it? The state machine that's run. We do not alter anything pretty much on the fly leading up to it. We of course control through ground control some of the levels to prepare the rocket for launch, but we don't update the software on the fly.
Okay. Another question in the chat. What time constants are you dealing with when sequencing? Are you dealing with microseconds, milliseconds, tens of seconds, that sort of thing?
Right. We operate at approximately 20-25 hertz loops for our commanding.
Okay. All right. Next question in from Leonidas. What's the standard you follow for the certification of the LAUNCHPAD software?
What standard? I forgot the name, actually. Let me look that up real quick. It's basically a standard, Doc 91710. And that document defines the range requirements, and then we've met with the staff to brainstorm again the hazards and what mitigations that we that would satisfy the reduction of risk.
Okay, great.
Mm-hmm.
We've got a few more minutes left for more questions. Gonna give just some brief time for more to come in if there's any others. Okay, another question from Brian. How do you map I/O points to messages? Do you have a template that generates code, or is it a code change every time wires get plugged in somewhere different?
We have both, basically, but we are evolving our system actually to be completely configuration based. So I would say right now we are configuration based, but it's a little painful to dynamically add channels, and we are working on upgrading our system so that we can affect only a portion of, say, one of the DAC servers have multiple hardware modules. We'd want to only take down the single hardware module involved in being reconfigured.
Okay. Mm-hmm. Next question from Colin Helms. Heard about Vera simulation part of ground software, and is it available by license?
I am not sure what that refers to. Vera simulation?
I think so.
Well, I don't think I mentioned that, but I'll look into it. I'll go offline for that.
Okay. Mm-hmm. Another question, is the data server only for storage, or is it in line with the store and lookup from the control consoles?
It's definitely in line. So it's I would say its number one responsibility is to take all of the data sources and merge it into a form that can be then distributed. All the ground software channels can be distributed from the data server to the consoles. And anywhere in the system, we would have access to any of the DAC servers or any of the servers channels.
Okay. Mm-hmm. And another question from Brian. What sort of delays and packet jitter are you able to tolerate?
I believe that we shoot for something on the order of 40 millisecond to 100 millisecond latencies. I'm not sure I understand exactly the question, but for any kind of tight control loop, for instance, you know, a local PID or control loop, we would run that custom per on the DAC server itself. So it would have access to its sensor data immediately. I would say that, and then that's within 10 millisecond or less, 1 millisecond sometimes, or sorry, 10 milliseconds is probably more appropriate. And then it would do local control there. So the only time we enter into a non-local control is when it's a very slow process, bringing up a temperature, bringing up a pressure, and in which case we can we can satisfy that in the normal auto sequencing. And then that's on the order of seconds, you know.
Yep. Okay, great.
These are good questions.
Give another minute for a few more to filter in. Great stuff. Great discussion so far. All right, Michael. Another question from Colin. Question on how to handle critical or hazardous commands in this architecture.
Critical or hazardous commands. Only thing I could think of is you know, we are fairly strict on who exactly would be able to make a, you know, to basically cause a command or a change in the system. And then our auto sequences are under strict and very careful review. And I believe we've attempted to identify all the edge cases, the hazardous cases, as part of our range review and certification process.
Okay. Colin, I think, clarified his question a little bit separately, such as for two-step verification for ordnance, for example, any commands associated with pyrotechnics, maybe.
Yes. Yeah, I have to admit I have a hole in my understanding with that part. So I don't have a good answer for him. Yeah, maybe I'll take that one offline.
Okay, we can continue the discussion on Slack there for any future discussion.
Sounds good.
All right, going to give just a few more seconds, see if any other questions come in. We got about 3 minutes left. All right. Michael, thank you so much for your time today.
Thank you, Brandon.
Like I said, we'll continue if there's any other discussion or Q&A on the Slack.
Excellent.
Thank you.